I've been reading the book Code, The Hidden Language of Computer Hardware and Software. In it, the author, Charles Petzold, explains how computers work starting from the basics. He covers the fundamentals of Boolean algebra and using very simple analogies builds a theoretical CPU from scratch. I've long been fascinated by this book and decided to return to it to see if I could use the examples to begin implementing a CPU of my own in code. One of the first examples presented is an 8-bit binary adder. Computer instructions and data are composed of binary bits that computers process by performing arithmetic, specifically addition. All other arithmetic operations in a CPU can be carried out using addition, so understanding how computers add is fundamental to comprehending their operation. It's easy to use a computer and consider its function to be magical, and in some ways it is. However, computers are made of actual hardware that other humans designed and built. Remarkable though they are, computers are far from magical, and are actually very simple machines, though comprised of billions of very tiny components. This is an image of a CPU that has been decapped, which is to say it's had its protective covering removed, exposing its internals. You can see the wires that bring in and carry out signals and the pattern of circuitry on the central block called the CPU's die. This is the Intel Pentium 5. This is a close-up of the die of one of the predecessors of the Pentium 5, the Pentium 3. Looking at it here, you might mistake the image for an overhead view of a city full of buildings and streets. It wouldn't actually be too terrible of an analogy, as CPUs work by controlling the flow of electrons through conductors on the die, much as vehicles and pedestrians are guided through the streets and sidewalks within a city. The flow of electricity lends itself well to the rules of Boolean algebra, which utilizes only two values, true or false. Similarly, electricity is either present and electrons are flowing, or they aren't. It's on or it's off, which can represent true or false, 0 or 1. As CPUs harness the movement of electrons to function, they are composed of billions of circuits called logic gates that control the movement of electricity. These gates can be used to perform the binary addition CPUs use to carry out operations, and are what the binary adder will be composed of. There are three fundamental logic gates, and others that are formed from combinations of these three. The first is the AND gate, so named because its output, labeled F, is only on or 1 if inputs A and B are both 1. Below the image representing the AND gate is a truth table that describes the AND's operation. As you can see, the only condition yielding a 1 or a true output is when A and B are both on. This is a code snippet from the binary adder I've built in JavaScript. This is how I've implemented an AND gate as a JavaScript function. If A and B are true, it returns true, otherwise false. Very simple. Next is the OR gate. The OR yields 1 if either or both inputs are true. It's only false if neither input is on. It's just as simple as the AND gate in code. Return true if A or B is true, otherwise false. The last fundamental gate is even simpler than the other two. This is called the NOT gate. NOT does nothing more than to invert or negate a condition. If the condition is true or 1, it makes it the opposite. Note that when this gate is combined with other gates, as we'll see later, it only appears as the little circle on the output side. Whenever you see it, it means the output of whatever it's connected to is the opposite of what it would normally be. It's very simple to express in JavaScript. If true, return false. If false, return true. Now we'll turn to look at the compound gates we'll use to build the adder, though there are others beyond those we'll see here. The first is the NOT AND gate or NAND gate. It's simply an AND gate with its output inverted. The effect of this is interesting as it makes the NAND gate the exact opposite of the OR gate, with it only yielding false if both inputs are on. I implemented it in JavaScript by passing the output of the AND gate into the NOT gate function and returning that result, which is an inverted AND. The other compound gate we'll use is the exclusive OR or Xor Gate. It's called exclusive because it only returns true if input A or input B is on, not both. Let's take a closer look. To achieve this effect, we need to use all of our previous gates. The inputs are fed into both an OR gate and a NAND gate. The outputs of these two are finally fed into an AND gate. It makes sense when you think about the description of an XOR gate. It's only true if exactly one input is true. In the diagram, the NAND is only false if both inputs are on. So, if the NAND is false, both inputs were on and we yield false regardless of the OR. Since the NAND will yield true even if both inputs were 0, we need to check if at least one was true. If that's the case, both the NAND and the OR will be on and the AND yields true. In the code, I just followed the diagram and returned the result of passing the output of a NAND and an OR into an AND. Now let's see how it relates to binary addition. Let's look at a simple binary addition problem. Just as in the decimal number system, where if the result of a column is 10, we write down the 0 and carry the 1 to the next column of add-ins, when we add two binary 1s, we yield a 0 in the 1's place and carry a 1 to the next column. So in binary, 1 plus 1 equals 1 0, or converted to decimal, 2. We can replicate this process with logic gates. We know that the results of an XOR is false if both inputs are on. This is equivalent to 1 plus 1 equals 0, so it would handle adding a column of 1s. However, we still need to deal with the carry. We do this by feeding the same input simultaneously into an AND gate. If they are indeed both on, it will yield true. With this combination, we can handle adding two binary numbers and any resulting carry. If there is no carry, the AND is false, and the sum of the column is a 1. This is great, but it misses one component. If we want to add multi-bit binary numbers, meaning there will be several columns, this construct doesn't handle bringing in a carry from a previous column. As such, it is called a half adder. Rather than the more complex diagram, we can instead use this simpler representation to indicate a half adder. Two inputs, A and B, two outputs, sum and carry. I represent this in JavaScript by returning an array of two items. The first the result of an XOR gate, or the sum, and the second the result of an AND gate, or the carry. If we want to be able to handle previous carries, we need a new construct that can handle a third input. Here we have a diagram of what's called a full adder. If you pay close attention, you'll see it's composed of two half adders with the carries from both input into an OR gate. If we take the diagram a section at a time, the logic makes sense. The XOR to the left will yield false if A and B are both on. We copy A and B to the lower AND, which would make it yield true, and turn on the OR indicating a carry. If there was a previous carry, the XOR on the right will yield true and a 1 will be placed in the column as the sum. This is the proper result for a column consisting of 1 plus 1 plus 1, as would be the case where a 1 were carried into a column consisting of 1 plus 1. This simpler diagram makes the logic clearer once you understand how the internals work. In code, I used two intermediate variables to hold the arrays yielded by the two half adders. This function definition simply follows the logic of the diagram. The two inputs go into the first half adder. The resulting array containing the sum and carry are stored in first half. The previous carry is then passed into the second half adder along with the sum stored in the first index of the array from the half adder. I then return the sum from the second half adder and the result of ORing the carries of both half adders. We can also represent the full adder more succinctly now that we understand its internals. In this format, it's easier to see how it's possible to wire many full adders together in series to add several columns of binary numbers. We use the simpler diagram to represent the internal workings of our 8-bit binary adder. A couple of things to note are that the carry in of the first column on the right will always be 0, so electrically it would be connected to ground as in the Petzold book. The input lines would connect to the switches, 2 per column, and each carry would feed into the next column's carry in. The sum lines connect to the lights as well as the final carry out line, which would represent the 256's place in binary, as the result of adding two 8-bit binary values could at most yield a 9-bit value. So let's have a quick look at the source code of the binary adder. The HTML is simple. The only displayable element present is the canvas element. I really enjoy working with the HTML canvas, as it's really just a blank slate where you can create anything you like. I set the size of the canvas and the background color and include a not available message for browsers not capable of displaying the canvas element. Below that, I include my JavaScript files using the source attribute of the script tags, then instantiate the adder application and call a method to set it up. The files adder.js and gates.js we've already seen. This is where I define the functions that perform the addition logic. The main file is app.js. I've added extensive comments to the source code of this file and posted it on my GitHub. There's a link in the description if you'd like to check it out. The most important aspects are the methods that get called when the switches are flipped by clicking them. The main method responsible is the compute method defined in the app class on line 207. The first thing I do is create an array called buffer to hold the results yielded from the adders as they go along, then a variable to hold carries. The lights are turned on by reading from their corresponding index within an array called outputs. I set up a for loop that iterates a number of times equivalent to the number of lights that might need turning on, or 9 times, one for each column and a final one for the carry light. Inside the for loop, the first thing to deal with is the hardwired 0 carry on the first column. The values represented by the switches are stored in two arrays named upper and lower underscore input. We pass the false and the inputs into a full adder and store the result in buffer. Then we write the sum, buffer index 0, into the outputs array at the index that matches the current iteration, which also happens to match the current column, in this case the first one, or column 0. Lastly, store the value stored in the second index of buffer, which is the carry value, in the carry value. Since carry and buffer are defined outside the for loop, their values persist until the function finishes. Subsequent iterations execute the code in the else clause and utilize the carry variable. When the compute method finishes, the lights will change their state according to what's been written to the outputs array, and we'll see the result. Let's test it out. Let's add 135 and 133. If we enter these values using the switches, we get 256 plus 8 plus 4, or 268. Great, it works. I went a bit overboard with the styling. Something I'd like to point out for those interested in web design is that I imported the font in the logo from Google Fonts. If you go to fonts.google.com and find a font you like, you can add it to your cart, so to speak, and get either a link to include it in your CSS via an @import statement, as I did here, or you can download it and install it on your computer to use locally. This is a great way to get unique and modern fonts for your design projects. My ultimate goal with this project is to keep reading the code book and implementing the interesting projects until I get a working, albeit pretend, CPU that can execute the instructions described in the book. If you're into computer internals or want to get into computer engineering, I encourage you to check out this book. Thanks.